Hello guys, welcome back to our channel. Today we are going to see what is a 2-bit magnitude comparator, how it works and how to make the Verilog code for this 2-bit magnitude comparator. A magnitude comparator is nothing but a electronic device which is used to compare the two bits or two or more bits. In this video we are discussing about the 2-bit magnitude comparator. So this comparator uh, will perform operation between the 2 bits. If we take the 4-bit magnitude comparator, then it will perform the 4-bit operations between the 4 bits. So let us see how this 2-bit magnitude comparator will work and how to design the logic diagram and how to make the Verilog code. So 2-bit magnitude comparator is nothing but, let us construct the first truth table for this. So here 2-bit, right? So we have a 2 bits A, B, and what are the combinations? A greater than B, A equal to B, and A less than B. So these three are possible for the magnitude comparator. So for 2 input, what are the possible combinations? 0 0 0 1 1 0 1 1, right? Here 0 0, both bits are same, so A equal to B is 1, remaining are 0, and 0 1. Here A less than B is right, so remaining are zeros. Here in the both bits A and B, A is the higher, so A greater than B and remaining are 0. And 1 1, here both bits are same, right? So here 1. So 0 0. Okay. This is the truth table for the 2-bit magnitude comparator. Okay. Now let us construct the logic diagram for this truth table. Here you can observe that A equal to B is 1 when both the inputs are same. This can be achieved by using the XNOR gate. We know that the XNOR gate, if both the inputs are same, then the output will be 1. Here the both inputs are both same, so the output is 1. So XNOR gate will be sufficient for A equal to B operation. For A greater than B and the A less than B, an AND gate with the inverter will be used. Suppose here you can observe that 0 and the 1, right? If we construct a AND gate with the NOT gate connected to the A, then we will get the output as 1. Let us see the logic diagram for this. So we have two inputs, right? A and B, right? So for A equal to B, we require one XNOR gate, right? So I am constructing this one XNOR gate. Okay, here nothing but this is XNOR gate. So next we require the A greater than B. So I considering that I am considering a NOT gate, and here I am considering the directly given to the AND gate. Here you can observe that here nothing but the A greater than B. If we give this is nothing but the A less than B. Okay, here you can observe that if A is 0 and the B is 1, then if we apply to the AND gate, then here 0 will be coming to the 1 and here the 1, so it will be activated. So for the A greater than B, the A will be directly given to the AND gate and the B will be connected to the NOT gate. So here we will get the output as A greater than B. Okay, this is the logic diagram for the 2-bit magnitude comparator. Let us verify this functionality. Suppose if we have a 0 1 inputs, so 0 1 inputs are applied to the 3 gates. Firstly 0 and 1, here XNOR gate, if the both inputs are different, then the output will be 0. So A equal to B is not correct here. So 0 will be applied to the upside. So here 1 1, the AND gate will be 1. So A less than B condition satisfies. Here in the same way, here 0 will be applied to the one of the input and 1 will be applied to the another input via NOT gate. So here input will be 0 and here input will be 0. So output will be also 0. So if A is 0, B is 1, here A is less than the B, so A less than the B output is logic high. In this way, this 2-bit magnitude comparator will be work. Now let us see how to make the Verilog code for this 2-bit magnitude comparator. Okay, now let's start making the Verilog code for 2-bit magnet comparator. So for that I am declaring the module with the name called uh, comparator. Comparator. Here we require inputs, right? Input. Here input is nothing but the 2-bit. So 2-bit means 1 is to 0. So A comma B. And if you consider the 4-bit, then the input will be 3 is to 0, that is 0 1 2 3. Here based on the number of the bit operation you do, you will declare here. Now we require three outputs. One is greater than, other is less than, and equal to. And these are the inputs and the outputs we require. Now I am using the always block, always at the rate. Either we receive the A input or B input, the operation will be begin. Now, what are the conditions? If A greater than B, if A greater than B, then begin greater than is equal to 1, 1B1. That means the greater than bit will be while, and remaining all will be 0, right? 1B 0 and equal to is equal to 1B 0. Okay, and ending this. Now, another condition else if A less than B, begin same conditions are there. Here now less than will be the high, logic high, because if A less than B, then the A less than B output will be high. I am ending this. Now another condition is finally if both the inputs are equal, then the equal to bit will be high. Now I am going to ending this module. Here begin and end module. Okay, this is the test bench code. This is the design code we require for the designing the magnitude comparator. Now let us write the test bench. So module TV. What are the inputs registered? 1 is to 0, A comma B. Wire. What are the outputs? Here you have to use output registered because we are using the behavioral modeling, right? So wire greater than, less than, and equal to. Comparator, comparator 1. What are the inputs A comma B and what are the outputs ZR, comma LS, comma equal to. Initial begin monitoring the values. What are the values? ZR is equal to percentage B, LS is equal to percentage B, and equal to is equal to percentage B. ZR comma LS comma equal to. Now I am giving the some sample inputs like A equal to some 5, B equal to 7, and hash 5. The hash 5 is nothing but the time delay. Now again A equal to 7, B equal to 5, and I'm giving hash 5. And finally A equal to 5, B equal to 5, and hash 5. Now I am ending this instrument by giving the command called hash finish and closing this module and end module. This is the test bench code required for our designing a magnet comparator. Now let select the tools and simulator, and I'm going to save this file and I'm going to run this. Here we have to give the name right to pitch magnitude comparator. Again I'm saving this file and I will run this. Yes, here you can observe that first input is a equal to 5, b equal to 7. That means a less than b. So here less than the output is logic 1 and remaining are 0. And in the third input, both inputs are same. So here equal to will be 1. So in this way, this magnet comparator will be work. Okay, this is the video for today. Thank you for watching this video. If you have any doubts, please mention in the comment section and stay tuned for the next video. Thank you.